Hello everyone. Hope everyone's doing okay. Hope everyone is finding all of the conferences very useful as we are finding them. Today it's my pleasure to introduce you to Dave Farley. Um, Let me just, yeah, there you go. Today it's my pleasure to introduce you to Dave Farley. He's a software consultant. This is the DevOps track, and today he's going to be speaking about taking back software engineering because craftsmanship is not enough. Um, hope you find this speak very useful. And just a reminder that this Tech Community Day event it's thanks to SQL Server Guatemala Group, Microsoft Dev Group Covan, Docker Guatemala, and Kubernetes Guatemala as well. We are all behind the backstage so that you can have so that you can enjoy all of the conference. This is our social networks. We have our webpage, and if you scan the QR code, you can follow us on multiple social networks, such as Facebook, Twitter, and YouTube. Um, and if you have any technical assistance you would like to have during this conference, please don't hesitate to send a message via the comments, and they will be addressing all of our questions at the end of his conference. So please don't hesitate. Also, if obviously if I'm talking English, you're probably not getting it, but I'm gonna talk Spanish just for a while. Si tienes alguna pregunta en español también puedes hacer la pregunta para Dave Farley. Y nosotros vamos a tratar de hacérsela llegar a Dave. Obviamente vamos a traducir, así que no dudes en mandarlos tu pregunta. It's a big pleasure to leave you with Dave Farley. He's, I believe, most of us that are in the DevOps world, we admire his work, we admire his career. So, with no more, any more taking Dave's time, I'm gonna leave you with Dave Farley and with his talk.
Thank you. Hello, everybody. So I started my career with job titles like junior software engineer and stuff like that. And if I'm honest, didn't spend any time at all doing anything that was even vaguely like engineering. And then during the middle part of my career, I had jobs that I worked for organizations that didn't really like the term software engineering very much. And we had jobs like software developer. I think one of the places where I worked, we had several grand wizards at one point. And then later in my career, I did some stuff that was really, really very hard, and it felt more like we were doing something akin to engineering. And really, that's the theme of my talk, is that I think that we've had a weird relationship with the term software engineering in our profession. And unlike pretty much every other field that I can think of, where engineering just means the stuff that works, in our profession, we've kind of lost track of what engineering means for us. And really, that's the kind of idea that I'd like to explore today. I think if you're anything like me, and when people use the term software engineering, you probably end up thinking something like this. And this is to software engineering what a soldering iron is to electrical engineering. This is not engineering. It's a tool. It may be a good tool, it may be a bad tool, but it is only a tool. This does not define engineering by any stretch of the imagination. In more recent years, we've started to take process a bit more seriously in software development terms, and we've come up with things like the Scrum process and other agile disciplines. And I'm a big fan of agile disciplines in general, and I think the Scrum process is an effective process. But have you any idea how many times the Scrum documentation mentions the words code or software? I will save you looking it up. The answer is 0 times. The Scrum process is effective at organizing teams to do things, but it's as applicable to plumbing as it is to software. So this too does not define what we mean by engineering in this context. In more recent times, an idea that's gained an awful lot of ground for some good reasons is the idea of software craftsmanship. So despite the slightly sexist term of craftsmanship, I'm going to carry on using that term because the alternative is a bit too awkward. But the craftsmanship is a big step forward over some of the other things that we've tried. But craftsmanship in general is limited to the quality of the craftspeople that are doing the work, and so that too doesn't really define what we mean by engineering. I think a good place to start thinking about this is to think about how we've produced things, during our history as a species on the planet. And for the vast majority of our history, everything that human beings created was as a function of craft-based production techniques. Later on, it wasn't until the mid 19th century and then through the 20th century that we started applying the mass production techniques to manufacture things, and then through the middle of the 20th century that we started using lean production techniques. Let's look at each of those in a little bit more detail. So craft-based production is art rather than science. There are no work standards, and each piece of work is individually crafted and so unique. The quality of what's produced is based on two things: the individual expertise of the craftsperson that's doing the work, and the limits of human dexterity and ability to manipulate tools or whatever else the things that we're creating the work of craft with. Engineering goes beyond craft. If you imagine for a moment a craft-built iPhone, it's a ridiculous idea. Something like an iPhone takes advanced engineering even to build a prototype, and engineering at that level goes well beyond the physical limitations of any human being. The precision with which something like an iPhone is created is way beyond even the most talented of craft people. We have a kind of an emotional link to craft-based work. I think if you're very wealthy, you might like hand-stitched leather in your car or something like that. But on the whole, craft is low quality compared to an engineered solution to things. The next step forwards is the idea of mass production. And mass production introduced ideas like assembly lines and standardization of components, standardized steps, and so on. The first example of mass production wasn't a production line for building cars like this picture. It was actually building rifles in the American Civil War. One of the horrors of the American Civil War was that it was the first war where they used mass production techniques to create the armaments. And there's kind of an amusing story, if you can have an amusing story about something as horrific as a war, but there's an amusing story about the man who wanted the contract for to supply the northern states with rifles. He went into Congress with a bag full of components, and he tipped those components out onto the floor of Congress and asked the congressman to select individual pieces from which he assembled a rifle. That was the first time where that was possible. It was the first time where the tolerances and the engineering were accurate enough to allow somebody to be able to do that. It requires these standardized components and precision, engineering precision, to be able to build those components accurately, sufficiently accurately that they will fit together. Before that, if you wanted a rifle, you'd go to an individual gunsmith and they would handcraft it from scratch, and your rifle would be unique. The next step on, which happened kind of just after the Second World War, was the birth of what later became known as kind of lean production techniques. And this was a mix of kind of Japanese approaches to thinking and industry, and an American man called Edwards Deming, who went to Japan to introduce more scientifically rational approaches to organizing work. Lean is about kind of producing quality items, right all the way through the process. It's a pull-based system rather than a push-based system. What do we mean by that? If you think about a production line, you manufacture all of the components and you get them to the place where you need to assemble things. That means that you have a large inventory of components. You're going to have big warehouses full of bits of cars, and you're going to have more of the easy to make things than of the hard to make things and all that kind of stuff. Lean is different. So you can think of that as kind of pushing those components down the line to the point where you need them. Lean is different in that you create the things that you need at the moment when you need them, and so you have just-in-time manufacture, just-in-time delivery, and all those sorts of things. Lean practitioners concentrate a lot on minimizing waste and all those sorts of things. There's another kind of take on this sort of stuff that's worth thinking about. I think one of the huge mistakes that we have made as an industry is to think of ourselves as having production problems and trying to apply the techniques of production engineering to software development. If you think about what software development is really like, if you're building something physical, going back to my example of an iPhone, if you're building something like an iPhone, then sure, the design of that thing initially is going to be extremely difficult. But the really, really hard problem is, how do you scale up the production of something like that so that you can create millions of them at a price? The production of physical things is a difficult problem. And so often when we talk about and think about engineering in the broad sense, what comes to mind is the idea of production engineering. Now think for a moment about what software is and what it's like. We never have that production problem, because however hard we work, if we produce a bunch of bytes that represents a computer system, we can always clone that collection of bytes essentially for free. So ours isn't a discipline that requires us that has production problems. Ours is a problem of learning and discovery, much more than that. To that end, it's worth thinking about the different kind of process models. And one of the disciplines that has a fairly rich model of thinking about processes in the abstract is chemical engineering, because that's what they do. And they have a taxonomy of different kinds of processes. And I want to quote from two. So here is a description of a thing called the defined process model. The defined process control model requires that every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. A defined process can be started and allowed to run until completion with the same results every time. That's fine. It's very nice if you've got that kind of process, but that doesn't sound anything like a description of what software development is like to me. So this is the territory of mass production techniques, assembly lines, and waterfall processes. These are very good at solving problems when you have a defined process model. Unfortunately, software isn't a defined process. We're always exploring, so these techniques don't really work in our world. Here's another process model. This is the empirical model of process control, provides and exercises control through frequent inspection and adaptation of processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. To me, that sounds much more like the kind of problem that we face in writing software every day. This is the territory of craft-based production, which is one of the reasons why software craftsmanship is a much better fit for what we do. But it's also the space for exploration, continual improvement, and lean process. So we can start, these are much better tools for software development than the things that were on the previous page. So where is the software industry? Where would we think that it is at the moment? It's not a mass production, and it never will be, because that's completely the wrong model for what software is. I would suggest that where we are is that we are a craft-based industry. You can see this for a whole variety of ways, but one of the ways is the huge variety in quality, productivity, approach, output, all of those sorts of things are just hugely variable between different teams, different organizations, different people even within the same organization. I think that where we should be aiming is to start applying more lean thinking. My favorite kind of soundbite for what lean is really about is that what we're really trying to do is that we're trying to get more for less work, trying to get more results for less work. And that's what lean really means. We're trying to minimize the amount of work that goes into doing what we need to do. The impact of software when we start applying engineering principles in software is quite dramatic. It's not tiny improvements in performance, quality, reliability, suitability of the things that we built. It's massive improvements, sometimes orders of magnitude better on a whole different range of different measures. So this is important stuff. This is worthwhile, and it's worthwhile thinking about and investing in to be able to do a better job. These are the kind of results that we would expect to see when we start applying engineering style thinking in other disciplines. I've been talking about engineering for some years now, and I've been involved in conversations at conferences and online and stuff like that. And I get involved in a rather surprising number of conversations about bridge building. Well, the way that usually goes is that I start spouting off and talking about engineering, and somebody says, "Yes, Dave, but software isn't bridge building." Well, of course, software development isn't like bridge building. But I think there are two problems with that observation. The first one is that usually what that means, so usually the mistake that those people are making is that they're thinking that bridge building is all about production engineering, which is true. If you're building the 100th or 1000th suspension bridge, then you can probably go and search the internet for a bill of materials for how that works, and you can probably get a Gantt chart that tells you exactly when the material should be delivered and all of that kind of stuff. It's a much simpler problem. But the other part of that is bridge building isn't always like that. If you're building the first bridge of a particular kind, that's going to be different. You're going to be building wind tunnels to try the bridge out. You'll be building models. You'll be doing maths calculations. You'll be trying to test the tensile strength of different parts of the materials and all sorts of discovery. And that's really the kind of engineering that I'm really talking about. Engineering is also not the same between different disciplines. Bridge building is not the same as production engineering for bridge building. Civil engineering is not the same as chemical engineering, which is not the same as aerospace engineering or car engineering or electronics engineering. Each discipline is different. They are distinct and have their own characteristics and their own behaviors. So one of the first things that we could think about in terms of what software engineering should really mean is that it's going to be unique to us. Software engineering is going to be our thing. It's going to be our discipline. It's not going to be the same as anybody else's. It's going to have its specific characteristics that are unique to us. There's another way in which not all engineering is the same too, is that engineering takes place at different scales. So here are two engineered structures. You can bet if the shed on the left-hand side of the screen was built by IKEA, then it will have been engineered to within an inch of its life to make sure it was using the minimum amount of wood for the price, to be able to hit the price point and all of that kind of stuff. But nevertheless, despite that, the engineering is so obviously on a completely different scale to construct that shed than the building on the right, the Burj Khalifa, the tallest building in the world. For that, they will have been breaking new ground for engineering. They'll have been trying stuff out that nobody's ever done before to be able to create a building on that scale. They'll have been doing earthquake simulations and material tests and finite element analysis and all of that kind of stuff. This is absolutely obvious when we look at these two buildings, that the engineering that goes into one is different to the engineering that goes into another. When we think about software, it's not always quite so obvious. To us, maybe it may seem evident that the level of engineering that needs to go into, I don't know, my mum's cake shop versus an aircraft control system or a medical device is going to be different. But to the average person observing the software from the outside, they're not going to see those differences. It's not quite so obvious, the differences, as it is when we look at these two buildings. So what is engineering? And as I said before, I've been having conversations about this, and I got involved in a Twitter conversation a couple of years ago. I've blanked out the person's name because I just completely disagree with what they were saying. But this person sent me a tweet and said, for me, engineering means working in a certified, inflexible process that includes planning ahead a lot, the antithesis of agile. I'm sorry, I just think that's nonsense. It's just not the case. And that doesn't represent the kind of engineering that I'm talking about. Engineering, would you say that, sorry, I'll just go back. Would you say that building something like the Curiosity rover was an exercise in a certified inflexible process that includes planning ahead a lot? I would not. That's an exercise in discovery, learning, evaluation. It's going to go wrong in lots of interesting and different ways as you go through. If anybody's currently following the SpaceX journey of trying to create the Starship online, you will see them currently blowing lots of space rockets up as they learn how to mass produce spacecraft. That's not an inflexible process that includes planning ahead a lot. That's engineering, as an exercise in discovery and learning. And that's what we're really talking about. So let's start looking at some definitions and going into this in a bit more detail. This is a Wikipedia definition. Engineering is the application of mathematics, empirical evidence, scientific and economical, blah, 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 blah. A whole bunch of words which tend to crop up over and over again in definitions of engineering along these lines. Here's another one, the science of making practical application of knowledge of the pure sciences. And here's a third, the application of scientific and mathematical principles to practical ends. So here's my working definition. This is what I mean when I say the words engineering. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. So from now on, when I say engineering, that's what I'm talking about in this context. So I said earlier, I think that one of the cornerstones of engineering is that it must be focused on learning. And I can't think of anything that for me would qualify as an engineering approach for software that didn't embody these 5 principles, which are really focused on making us great at learning. So let's start walking through those one at a time. So first, iterative. Iteration, the act of repeating a process either to generate an unbounded sequence of events or to focus on an outcome. Being iterative means that we can learn, we can react to what we look for, to what we learn, and we can adapt to what we've learned. It's absolutely fundamental to any process of learning to be able to try things out, go around in circles, cycle around and focus on what we can do. Being iterative also allows us to steer towards a goal. You don't navigate from one place to another by just taking a bearing and driving in that direction. You steer and you correct and you react to what you're observing. My favorite soundbite for describing agile approaches to software development is inspect and adapt. And something like, navigating towards a goal is precisely what we're talking about. Being iterative is also fundamental to any process of kind of continual improvement, where we are looking to refine and improve and refine and improve and refine and improve. That's how organizations and individuals and teams get to do great things, by continually improving and refining their skills, techniques, and understanding. And it also allows us to, through practice and repetition, to get really good at the things that are important to us. We can hone those skills and techniques and get better and better at whatever it is that matters to us. But being iterative is kind of the cornerstone for all of those advances. The next in my list of 5 is the idea of feedback. And Wikipedia defines that as information about actions returned to the source of the actions. It means that we can observe the impact of our choices, and we can use the feedback to build our understanding and to learn. I tend to use this little diagram as a schematic for continuous delivery. At the outside of this feedback loop, we go from idea to working software in the hands of users. And at the inside of the feedback loop, we do the very, very fast cycle of test-driven development. And in between, we use acceptance testing and behavior-driven development to evaluate the quality of our code. But even just for continuous delivery, there are many, many, many more feedback loops than that. Feedback is absolutely essential to our ability to learn, because it's the thing that delivers information on which we can make decisions back to the point at which we need that information. The next of my 5 is incremental, and a particular take on incremental. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application in which components can be freely substituted. Incrementalism and modular systems kind of go hand in hand. And my wife says that I'm a serial nerd, but she's mistaken, because I'm a parallel nerd, because I can be a nerd on multiple fronts at the same time. So I'm going to demonstrate one of my nerdisms, which is software engineering and software development, with another, which is aviation and the space industry, and in particular the Apollo program. So this is the Saturn V rocket. This is the spacecraft that took human beings, in this case men, to the moon and brought them back safely. And this was a modular system. There are 2 key components here, and then we'll break in. So the first part of the spacecraft, all of this is just to get the rest from Earth to Earth orbit. When the Apollo program was starting, they didn't have this in mind. They had a kind of one stage to the moon picture, a kind of kid's storybook picture of space rockets taking off from the Earth, flying to the moon, landing on the moon, taking off from the moon, and flying back and landing on the Earth. But that doesn't make sense energetically to solve that kind of problem. So instead, you break the system down into a series of modules. The second set of modules are the spacecraft that actually do the rest of the journey. And that was described into 4 large-scale components. Here's 2 of them. So this part of the spacecraft, its job was to get the human beings from Earth orbit back to Earth, primarily. It's also kind of the place where they lived on their journey. And the second part of the spacecraft is the service module, and the job of that was to get everything from Earth to the moon, and from the moon back to Earth. And then once they got to the moon, there were these components, these modules, and this too are 2 key modules. This is the lunar module, is the whole lot, but this is divided into 2 pieces. The lunar ascent module, its job was to get 2 astronauts standing up from the surface of the moon into lunar orbit to rendezvous with the command and service module. And the bottom part is the lunar descent module. Its job was to get these 2 components down from lunar orbit down to the surface of the moon. Now, the modularity of these systems, as I said, wasn't what they had in mind at the start, but was absolutely crucial to the success of the missions. One of the benefits of modularity is that it gives you more options. You can recompose the modules in different ways. So when the service module essentially blew up and lost all of the oxygen and life support systems, they were able to repurpose the lunar module as a lifeboat, and because of that, it saved the life of the astronauts and brought them back to Earth when the Apollo 13 disaster occurred. So modular systems are give us a way of composing them and using them in different circumstances. The other thing about modularity that's important is that it allows different organizations, different teams, different groups of people to work on different modules. So in this case, in the spacecraft case, there were completely different companies that were working on different parts of the systems. The Grumman would built the lunar map, the lunar module that you see here, but a different part of the American aerospace complex built the rest of the spacecraft. But it was farmed out to different organizations, and that's possible only when you've got modular systems. Modular systems allow us to work in smaller units. We can make change in smaller steps, and that gives us the ability to make progress quickly and more simply. It allows us to compartmentalize the problem and focus on within those compartments, but it also reduces risk. If we work in a series of large, complicated steps, the risk of releasing those changes is huge. If we can decompose the problem down into a series of small steps, the risk is kind of shared out between all of the little steps, and the risk of any one of those changes is lower. Now, I've used two words that in the English language sound quite similar, and the best way of kind of seeing the difference that I know of, I've stolen from a friend of mine, Jeff Patton's book, User Story Mapping. So this is iterative. You start off doing a rough sketch of whatever it is that you want to do, and then you refine the quality of that sketch over time until you get to a desired result. Being incremental is more like this. We do work in one area of the system, and then we do work in another area of the system until we've got a whole system. So these are both different and complementary approaches. Again, if we're thinking about engineering, I think you would agree that we must have both of these approaches as kind of key cornerstones of the way in which we start work on big, complicated systems. The fourth of my 5 things is being experimental. And Wikipedia says an experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. Being experimental, I'm going to tell you another story based on the space race to kind of demonstrate the importance of experimentation and kind of just position what it is that we're talking about. This picture on the screen, this is John F. Kennedy, the American president in the 1960s. And he famously stood up in front of the American Congress and made this speech: I believe that the nation should commit itself to achieving the goal, blah, 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 of sending a man to the moon and returning to Earth. He said this in 1961, 2 weeks after the first American was launched into space. The first American in space was a man called Alan B. Shepard, who was incredibly brave because at this time in history, America's spacecraft were pretty ropey. They were pretty dangerous. And Alan B. Shepard's space mission was him sitting inside a large tin can strapped to a top of an intercontinental ballistic missile and called the Redstone booster. And the Redstone were blowing up all of the time on launch. So Shepard was this ridiculously brave man. He was launched 100 miles up and then parachuted back down, didn't go into orbit. 2 weeks later, Kennedy's saying, let's send men to the moon. You can kind of imagine that, you know, he's kind of done what politicians and people like that do. He's kind of painted this vision and then said, oh, you know, I'm a politician. I have no clue how to solve this problem. You're smart. Go and figure it out. But he's kind of painted this vision. And that's to be fair, that's his job. You can kind of, at this point in history, these are the things that they didn't know how to do. They hadn't got takeoffs sorted. Their spacecraft were blowing up on launch. They hadn't got multi-stage launches sorted either. The re-entry wasn't really reliable. The return of the spacecraft in the next mission after Shepard's, Gus Grissom's capsule sank and was lost. Nobody had done a spacewalk yet. They hadn't got spacesuits that would allow people to do work in a vacuum. They had pressure suits from aviation, but at this stage in history, they hadn't really got spacesuits that you could do a spacewalk. The first person to do a spacewalk nearly died because the spacesuit blew up like a balloon, and he couldn't move to get back in the capsule very well. They hadn't got mission control sorted. Nobody had docked two spacecraft together. All of these things were unknown territory. So what do you do when you're faced with a problem on this kind of scale? Well, one thing to do is to hire some really smart people. This is one of those really smart people. This is Margaret Hamilton, who led the team that did the flight control system. She worked at MIT, and she was the first software engineer. She invented the term software engineering because she believed that what they were doing was engineering. Up to that point, everybody thought that it wasn't engineering. It was just, that's what you did after you did the real engineering, is write the software. Margaret started taking this stuff seriously and applying engineering style thinking to solving the problems, which famously kind of saved the Apollo 11 mission when her system shed load when it should. So you're in NASA the day after Kennedy's just made his famous speech, and you're trying to figure out what you're going to do. How are you going to do this? How are you going to cope with this problem? One thing is to really start thinking about the nature of the problem. So here's a picture of the Earth-Moon system. Except this isn't a picture of the Earth-Moon system, really. This is a kid's storybook picture of the Earth-Moon system. This is the Earth-Moon system to scale. At this point in human history, no human artifact had been more than 1 pixel away from the Earth. So, first problem, how do you get anything all the way from the Earth to the Moon and back again? How do you do that? You can kind of imagine the conversation in NASA the day after Kennedy's talk. What are we going to do now? How on earth are we going to solve this problem? He's just said we're going to go to the Moon in 9 years. How are we going to do that? We're nowhere close to being able to do that. Oh, no. Oh, my brother-in-law's got a car showroom. Maybe we can get a job there. No, let's see if we can at least think about this problem. Where would we start? I know, I've got an idea. Why don't we build a spaceship, put the astronauts in it, send them to the Moon, and see if they come back? So no, this isn't the time for waterfall thinking. What else could we do? Well, we could build a spaceship, not put the astronauts in it, send it to the Moon, and see if it comes back. Well, that's better. It's not going to kill quite so many astronauts, so that's a step forwards. Is there anything that we could do that's simpler than that? Oh, wait, I've got a great idea. Why don't we build a spaceship, send it to the Moon, and just land it on the Moon? We don't bring it back. That would nearly halve the problem. That is a great idea. Why don't we do that? That's fantastic. We would learn loads if we could do that. What does landing on the Moon mean? Well, it doesn't have to survive the landing on the Moon. And that was the job of this space program. This is the Ranger program. These were literally spaceships as bullets to carry out target practice to see if you could hit the Moon. So the job of this program was to try and hit the Moon with the spacecraft. So how did that go? Ranger 1, it blew up on the pad. I warned you that their launches weren't really very reliable at this point. Ranger 2, it blew up on the pad again. Nevertheless, they had learned some things. Ranger 3, it got into lunar orbit. Sorry, it got into Earth orbit, did the deorbit burn, and then missed the Moon completely. Ranger 4, it got into Earth orbit. It did the deorbit burn. It shot off towards the Moon. It hit the Moon, but all of the systems had failed as it left Earth orbit, and they were able to track it from the ground, but they didn't have any information. They didn't have any data from that experiment. Ranger 5 missed again. Ranger 6, it hit, but the cameras failed. So they got telemetry, but no pictures. Ranger 7 was a success. Ranger 8 was a success. Ranger 9 was a success. So you're NASA in the Cold War with effectively an unlimited budget. This was the major focus of the politics of the time and the engineering of the time. You've got access to some of the smartest people in the world. Where do you start? You don't start by drawing a Gantt chart and doing a 9-year plan. You start by carrying out a series of experiments, and those experiments do and will go wrong. So you're going to work in a way so that the failures don't cripple your ability to make progress. At each step, though, you're going to learn new things. If they just launched this and it had all worked, they would have learned first time, they would have learned less than going through this process and refining it. The second time, it probably would have failed. So failure is not a big problem if you're able to learn from it. Here's another simple example of being experimental. So you might have seen things like this before, but the game here is to decide which of the orange dots is larger. Is the orange dot on the left bigger? Is the orange dot on the right bigger, or are they both the same? So think about your answer, and now we can carry out an experiment, and they are in fact both the same. If you said they're both the same, it probably means that you've seen the picture before. Let's try another one. So here's another one. So predict, so make your judgment, which line is longer? Is the line on the left longer? Is the line on the right longer? Or are they both the same? My guess is that lots of people say they're both the same because they've seen this before, but actually the one on the right is longer because I made it longer. You can't tell without carrying out the experiment. The measurement is important. Being experimental is about not fooling ourselves. We as human beings jump to conclusions all of the time, and science and engineering are really our way to avoid fooling ourselves. And so being experimental and carrying out the measurements is really central to our ability to make well-reasoned, defined progress. The last of my 5 things is being empirical, based on, concerned with, or verifiable by observation or experience rather than theory or logic. Being empirical is important. It means that we can make decisions based on evidence. We can disambiguate myths from reality. We can start applying real scientific style reasoning to our problems. We can never, ever be certain of success. However good our theoretical models, we're always going to try them out. That's what engineering is. Progress only comes when we risk failure. If we know for sure that something's going to work, that's not an experiment and we're not really learning. We learn most when reality doesn't match our predictions. This is one of the beauties of scientific thinking. At the point at which our experiment just fulfills our expectations, okay, it's kind of nice, but it's the moment when the experiment doesn't match what we expected that we're really learning. Now we're breaking new ground. Now we're really deepening our understanding of what's going on. Production in software terms is always going to surprise us. Putting our stuff into the real world is going to be a different kind of test to anything else. And it should. We should be learning from that exercise. A nice way of thinking about this, I think, is that all of our design choices, all of our code, all of the tests that we write, the documentation that we write, the ideas in our heads are only really our best theories to explain things so far. And our job as professionals in this space are to refine and improve our theories all of the time. Again, this is kind of a lesson that we can learn from science. One of my other nerdisms is that I'm an avid reader of physics in my spare time, and general relativity is the most beautiful, amazing theory about the way that bendy sheets of our universe is made up of bendy sheets of space-time, and it predicts things like black holes and all of this amazing stuff. And yet we kind of know it's wrong, and that there are teams all around the world that are funded working to try and find a better theory, because general relativity doesn't match up with the other amazing theory quantum theory. So science is always refining and learning and incrementally just taking a step forward and a step forward. We should be looking to do the same in the systems that we build and the way that we approach things. So my 5 principles for engineering, they need to be iterative and employ feedback. But these, sorry, I was ahead of myself. I would just like to position continuous in delivery as an engineering discipline. Continuous delivery is deeply iterative. It's built on the idea of optimizing for fast, high-quality feedback. It encourages and is built on the ideas of making small incremental changes. It encourages and facilitates our ability to experiment, not only in the form of automated tests within our deployment pipelines, but going out to experiment with ideas like A/B testing and canary releasing into production. And it's empirical. We're going to gather that telemetry and that data from production and learn and refine our practice all of the time. We're going to use these sorts of techniques to improve and get better all the time, and the sort of feedback model I talked about before. Fundamentally, though, for today, this is what I'm really talking about. And if you've been paying attention, you will recognize this, I am sure. This is the scientific method. This is the thing that differentiates our high-tech civilization from all of the civilizations that went before. We're going to make an observation of reality. We're going to propose a theory to explain what we see. We're going to make a prediction based on our theory, and then we're going to carry out an experiment to test the prediction. And we're going to then loop around and do this again and again and again. This is humanity's best problem-solving technique. And I believe we should be doing more to try and apply this kind of thinking to solving problems in software. In software development, we've learned that design, development, and tests are not discrete stages that we need to perform one after another. Rather, they are continua. We need to be doing all of these things all of the time in order to do them in order to do any of them effectively, and in order to learn what we're doing. So we're going to spiral around doing all of these things iteratively. We're going to incrementally build up the quality of our stuff, of our systems, and we're going to gather the feedback from here. We can measure the efficiencies of our processes by looking at ideas like lead time and cycle time to see how efficiently we're going. And we can then, the real value of this kind of model, though, is that we can start experimenting. We can have a theory, we can make a prediction, we can go out into production, and we can evaluate our prediction. Did that change actually mean that we increased the number of users, or made more money, or delighted our users more? And then we can do other kinds of experiments. We can have a theory and make a prediction, carry out an experiment in the form of an automated test, which we can evaluate within our deployment pipelines. This is a picture that I use all of the time to talk about continuous delivery. This is really what continuous delivery for me is about. I would argue that continuous delivery is a genuine first-class software engineering discipline, applying the kind of deep engineering principles that we've been talking about today. One thing before I wrap up, sometimes I get a pushback at this point in terms of as though I'm dissing craftsmanship, and I'm not. Craftsmanship is a good thing. It's about skill, creativity, freedom to innovate. It promotes ideas like apprenticeship schemes. But I can change. All of these things are important to our discipline. But this is equally true of engineering. I can say exactly the same things of engineering. All of these things are important for an engineering discipline too. So this doesn't reduce the level of craftsmanship and creativity. It improves upon it and increases it. Engineering adds to craft. It doesn't diminish from it. It improves repeatability. It provides guidance and structure. It improves quality. It improves efficiency. And it allows us to make progress even when we are otherwise stuck, because it can guide us on how we should be thinking about problems. In our industry, we often talk by analogies. And in this case, I am not doing that. I am not saying, let's be like engineers. What I am saying is, let's take back ownership of what engineering means for us, and let's be engineers. Let's start applying those kinds of scientific disciplines to solving the problems that we face. Thank you very much. That's my talk. I think we have a few minutes for questions.
Thank you very much, Dave. That was one of the most engaging speaks that I've ever heard, and it's very inspiring. So hopefully we have, hopefully we have a few questions out there. If you don't mind, attendees, to send your questions in the comments section. We can have the questions answered by Dave. So are there any questions?
Daremos un espacio a todos, a todas las personas que nos estén escuchando o que nos estén viendo en vivo para que puedan hacer sus preguntas a Dave. Si lo hacen en español, no hay problema. Nosotros vamos a procurar trasladar su pregunta al inglés y tal vez poderle dar una explicación en español si fuera necesario.
All right. I believe I have a personal question based on the talk, and perhaps that way we can open it to more questions.
Sure.
How do you address, like, for example, here, at least in the region, in the Latin American context, one of the few, like, let's say, industries that are have the most resistance to change, and what we already heard, it's the fintech. For example, banks and things like that. And most of our attendees, if I'm not wrong, probably, I don't know, probably 30%, I'm probably wrong on that, but they have experience working with fintechs or with banks. How would you address these type of change in mindset, for example?
I make a living as a consultant these days, but before that, the last 10 or 15 years of my career, I spent working in finance and applying these kinds of approaches in finance. I was involved in building one of the world's highest performance financial exchanges, and we applied these techniques. I think that applying these kinds of engineering disciplines in fields like finance are deeply important, because it's my opinion that you can't be genuinely regulatory compliant unless you apply these kinds of disciplines. I now have quite a lot of experience of guiding companies to do this, and big banks across the world, big fintech organizations, are applying these kinds of disciplines to their work. Now, how do you start to get people to think differently about these things? That's a huge challenge, but it's part of what I do for a living. I think you need to think about performance on multiple fronts. You need to think about performance on the technical front, which is a lot about the engineering stuff that I'm talking about, but also on the organizational front and on the cultural front. We need to think about these things differently and apply different kinds of thinking to solving these sorts of problems. In order to be able to get the freedom to make those sorts of changes, that's a long-term project, and you've got to win hearts and minds in different ways. For technical people, the arguments from data are good. I would point people in the direction of the State of DevOps report, where there's some data that some of the data that I presented in terms of software project performance was from there. So look at the State of DevOps report. If you Google for that, you'll find data on software project performance. And that data is across all different kinds of industries. For other people, you need to get more commercial, more emotional engagement. One of the ways of thinking about that, again, we can look at the data for this, but organizations that practice continuous delivery and its associated disciplines, on average, make more money than organizations that don't. So a fairly good argument, if you're going and trying to convince places like banks or fintech organizations, is, would you like to make some more money? Would you like to build better software faster? Because we know how that works. Forgive me for advertising, but if you're interested in, I'm going to be doing some more stuff on something that I call continuous compliance on my YouTube channel. So if you're interested in this topic, go to my YouTube channel, which is called Continuous Delivery. If you search on YouTube for Continuous Delivery, you should find my channel, and you're going to see some more stuff on these kinds of topics there.
Thanks, Dave. Alberto Reina says, great talk, and thank you.
Thank you.
And we have one more question from David Ayala, who says, how can you promote your team to develop this attitude, I will say, to become an engineer instead of just act like one?
So I think part of this is to genuinely start thinking more scientifically, start applying that kind of thinking. And I'm sorry to keep pushing my YouTube channel, but do go there, because that's kind of the real underpinning theme of all of my stuff. So how do we apply science to solving problems in software? That's part of it. I think the thing that differentiates craftsmanship from engineering is really about measurement and how do we evaluate things. So what sorts of things can we measure? How do we control the variables so that we can eliminate all of the stuff that doesn't matter and focus on the stuff that really matters? And that starts getting you into ideas like, high levels of automation that is common with continuous delivery, infrastructure as code, automated testing, automated configuration management, all of those sorts of ideas that allow you to control the variables. And then you look to you can just evaluate the things that you want to do. One of the tricks, so I give you a little trivial example. So I write software by doing test-driven development. And that means that I write the test first, and then I run the test and I see it fail, and then I write some code to make the test pass, and then I refactor the code and the test to make them great, and then I commit. And that's how I proceed with software development. When I'm working like that, when I write the test, my first act is to, once I've written the test, is to run it and to expect it to fail. What I do personally is I sometimes say it out loud, but if I don't say it out loud, I say it in my head. I state what I expect the error message will be when my test fails. And if my test fails with a different error message, it means that my experiment has failed and I made a mistake in writing my test. That's a tiny little experiment. It's got all of the 4 stages. The test is kind of the characterization of the problem. The hypothesis is that when I run the test, it's going to fail with this particular error message. I execute the test and it fails with that error message, and that's good, and I can move on. That's the result of my test. And if it doesn't, then I've made a mistake in the test and I can go and refine it before I make any more progress. So that's the kind of tiny, very, very fine-grained engineering practice that makes a big difference day to day in your work. And then you start applying that on broader and broader fronts to wider and wider areas of your work.
Great. Thank you very much, Dave. I believe we have another question from our collaborator here, Alvin. The question is, what is the key to being a good engineer? And thank you very much for the talk. It was excellent.
Well, thank you very much. I think there are a number of keys to being a good engineer. One of the ones that I mentioned during the talk that I'm kind of a popular science nerd. I like reading about physics, and one of my heroes is Richard Feynman, who spoke beautifully about physics and science, as a philosophy of science kind of thing. One of the things that Feynman talks about is the being experimental, and if you guess that if you get, it doesn't matter how smart you are, if you guess and that guess can't be backed by experimental evidence, then it's still a guess. So trying to work as a series of small experiments is kind of part of that. But there's more to it than that. And one of the other things that Feynman said is that science is about the ignorance of experts. So it doesn't matter how famous somebody is. if they're telling you something, you should always look at it and evaluate it with a skeptical mind. Does the thing that they're telling you stand up? Does it sound as though it makes sense? And then go and try it out and figure it out for yourself. I might be well known for writing books and talking at conferences, but you shouldn't take my word. I might be talking rubbish. So try out my ideas, figure out whether they seem to make sense. If they sound reasonable to you, figure out how you could find out how to do it better. And I think that kind of skepticism, I think there's a degree to which our industry is a little bit too much like a fashion industry sometimes, and we kind of go from idea to idea just because it's popular, rather than focus on the slightly more deeper, slightly more meaningful things that are more durable. So I think being a good engineer is about being disciplined in approach and taking these small experimental steps, but also being reasonably skeptical about any idea wherever it comes from. And your first response to any problem that's posed to you is, how could I test that? How could I figure out whether that was true or not?
Thank you very much, and thank you, Valeria, for your question. Give me 1 sec. There you go. Another question will be, what is the role of measurement? Because oftentimes we are most focused on developing software or developing, let's say, whatever we think it's cool or it's at hype at the moment. But what's actually the value of measuring? Like, how can you advise, like, okay, you need to measure because, I don't know, blah, blah, blah.
It's a good question, and there's, if we're going to take this stuff seriously, then we've got to approach measurements on a broad number of fronts. One form of measurement we've already talked about, the kind of tests that we create. We're going to express what we think the desired behavior of our software is going to be, and then we're going to evaluate whether our software actually fulfills that. That's a form of measurement, and using automated tests to drive that kind of design is part of that for me. There's a broader picture though. I mean, software projects are kind of famously difficult to measure in terms of performance. It's very difficult to know whether your software project is outperforming my software project because you're smarter, or because you're using better tools or better techniques, or maybe your problem's simpler. We don't know. It's very hard to do these sorts of things. In more recent years, so there's been lots of kind of surveys of software projects over the years, but in more recent years, the State of DevOps, the people behind the State of DevOps report and the book called Accelerate have come up with a model that allows us to, with some degree of scientific validity, statistically accurate correlations between different kinds of behaviors, and they can categorize teams based on these measures. And the measures that they use are stability and throughput. Stability is a measure of two things. So it's the number of defects that you get at this point in the process, and how long does it take you to fix the defect at that point in the process when you find one. And throughput is, and that's a measure of the quality of your output. How good is the stuff that we make? And then throughput is about lead time. How long does it take you to go from commit to deployable software that you can kind of present to a user? And how frequently are you able to do that? Those are the two measures of throughput. And that's really about efficiency. So they're not perfect in every regard. They don't tell you everything that you would like to know, but they give you a measure of the quality of your work and the efficiency with which you're able to produce work. And you can use that then to evaluate almost anything else. If I decide I want to adopt a new language, does that make me produce stuff with fewer defects that allows me to fix them more quickly? Or does it allow me to make software more quickly and more efficiently and deliver it more frequently? I can carry out an experiment against that. If I want to reorganize my stand-ups, does that move the dial on stability and throughput? And so on and so on. So there's a whole model built around these, which I very strongly recommend that you look into the State of DevOps report and the Accelerate book by Nicole Fosgren, Gene Kim, and Jez Humble. that outlines this kind of scientifically valid. It's kind of using sociological techniques for analyzing the data that they've got from surveys, which is unusual. Most software performance surveys aren't as rigorous as this. And they've got this kind of correlative model that can differentiate. If you do these things, there's a relationship between the kind, if you do these things, you will be high performing. If you are high performing, your company is making more money. If you are high performing, your developers are having more fun. If you're high performing, your users are liking what you're making more. So all of these things, they're related, and now for the first time ever, we've got this model that we can kind of predict some of those things. So looking to some of those are useful measures. It's very easy to get inappropriate measures. One of the commonest ones at the moment is chasing test coverage. I am a card-carrying, test-driven developer and a strong believer, but I think it's a mistake to chase test coverage for the sake of it. It leads to all sorts of bad behaviors, for example.
Thanks, Dave. We have another question, and it's from Steve Jones. It says, how do you think about experiments and iteration with data? Because I need to maintain state.
Yeah, so me too, mostly on the software systems that I've worked on. So I think that data needs to be part of the deployment pipeline. I think you need to be carrying out continuous delivery for data changes as well as everything else. The one caveat that I have is when you start talking about machine learning systems, because I don't have a lot of personal experience with machine learning. I am in the middle of working on something with somebody who is an expert on machine learning to figure out how you can use these sorts of apply these sort of engineering thinking to development of machine learning systems. So not really ready to talk about that stuff. But if you just mean regular data, then yeah, so you need to take data migration seriously, you need to take automation seriously, you need to control the variables around that stuff. And again, I'm sorry to be advertising, but keep an eye on my YouTube channel because I intend to be doing some stuff on the YouTube channel about data migration over the next few weeks.
Also, we have another question from David Ayala, who's asking, do you think tooling is a game changer in the process to become better engineers? Or is it more about the process?
Sure. So I think it's more about the. I would avoid the word process and say it's about the philosophy. I think that this is deeper than only process or tooling. It's a mixture of all of those things. The way that I talk to my clients about it is that I tell them if they want to become good at continuous delivery and this kind of engineering discipline, they have to focus on technical performance, organizational performance, and cultural performance. You need all three of those dimensions addressed to be good at this stuff. So continuous delivery in particular is deeply about high levels of automation. So the tooling's kind of important. But at the same time, which tools you pick matters much less than how you use them. I've been doing versions of continuous delivery for nearly 20 years now, and in all sorts of complicated environments usually. And I've used all kinds of different tools, but certainly for the vast majority of that time, mostly we built our own tools because there weren't things that were off the shelf. And it's not that hard. The tools aren't the real problem. It's the way that we use them. We've had the tools that would do this stuff for way longer than we've been doing it. You need a version control system. You need some kind of scripting platform. And it's a bit easier these days with web technologies. And that's about it. So the cloud's nice. The cloud's nice. It means that we can scale things more elastically and all that kind of stuff. But none of those, but those things aren't essential. So the tools have been around since the, 90s at least, to be able to do this kind of stuff. And so tooling isn't the slam dunk problem. Having said that, the tools are getting better and better all of the time. So the modern continuous integration tools are better than the early generations of integration tools, but none of them yet are what I would think of as slam dunk. There's no tool that I can hand on heart point to and say, if you go and choose that, it's gonna solve your problems, because it's much more complicated than that. It's about the way that we choose to work and the way in which we design software and the way in which we evolve it over time, and all of those sorts of things is equally as important as just the tools that we use.
Okay, thanks, Dave. We don't have any more questions at this moment. So I think I will proceed with a personal and part from my community question. Something that I've seen a lot of times, that people actually doesn't take care of the part of studying things, studying the science behind writing software. And I would like to explain from your perspective, how important do you think is to study the things behind software, to actually know how the things work, not just write code in your career?
I think that's kind of a leading question, because you know that my answer is going to be, I think that's just deeply important. So I think that we get hung up on the wrong stuff very often, and I'm actually in the middle of writing another book at the moment, which is kind of on this topic. It's kind of exploring the idea of software engineering and what that really means. And I think that one of the kind of sound bites, one of the ideas that kind of started me off on this book, I was having a conversation with somebody, and we were talking about what the durable ideas are in software development. What are the things that are kind of core ideas, principles that are common to all of us in the work that we do? And my 5 things, my iteration, feedback, experiments, and so on, is one set. Those are the 5 things that are focused on learning. But there's another bunch of 5 things that, to me, it seems whatever language you're using, whatever framework you're using, are profoundly true and have been true all through my career, 40 odd years, and will be true for another 100 years. And that's the ideas that allow us to build systems that are bigger than the capacity of our head to hold. So managing the complexity of the systems that we build. And I think software development is world-class difficult. It's one of the harder things that human beings do. It's up there with hard parts of physics and stuff like that. It's a deeply difficult thing, and yet we don't tend to apply the same kind of disciplines and thinking to solving problems in software very often. So I think that we should be teaching people, profoundly, to learn the lessons that are always true. So the things about iteration and feedback and experiment, and the things about modularity, separation of concerns, cohesion, high cohesion, abstraction, and information hiding, and loose coupling. Those things, to me, seem fundamental in everything that I've ever done in terms of software development and design. If you're on top of those things, you have a much better shot at building decent systems. If you ignore those things, you're going to be building crap. And so those things seem much more important to learn. For some reason, our industry, I can be a grumpy old man because I'm an old man and I'm a bit grumpy. But as a grumpy old man, my observation of our industry is that we get too hung up on fashion. How many times have you had an argument or a debate about which language is better, or which editor is better, or which framework is better? I'm past caring. I don't really mind. Through my career, I've probably learned 20 or 25 different programming languages, and I've got ones that I'll go to, for others. But I don't think the difference between them is significant enough to matter in terms of being able to build better systems. My observation is that a great programmer will be great even if he starts off in a language that he's never used before. In a week's time, he'll be great in that language. And so there's something more. There's something deeper going on than just the tools that we use, just the language. And it's this other stuff. It's about learning to be world-class at learning, and that's about science, and world-class at managing complexity, and that's about things like modularity and separation of concerns, and so on and so on and so on. And so those things seem to be the durable things, and it disappoints me that those sorts of learnings aren't sufficiently taught or pushed in our educational institutions and when software developers are kind of new to the profession.
Yeah, thank you for answering, David. I think that was nice for me and for my community. We don't see any new question on what channels, so I think we can close with the session. And thanks to you for all your presentation. As Marcus said before, it was one of the most entertainment sessions that I've ever seen. I think a lot of people learn a lot today, so thanks.
Thank you, and thank you very much for asking me. I hope everybody has a good time at the conference.
Thank you very much, Dave. Really appreciate it. Just a reminder that our next session will be WSL2 and Docker to develop embedded Linux containerized applications. That's coming from Canonical developer advocate, Hayden Barnes. Just scan the QR code in order to continue and do not lose track. A reminder that Tech Community Day, it's hosted on June the 12th and 13th, so today and tomorrow. And it's brought to you by the community, for the community, by SQL Server Guatemala Group, Microsoft Dev Group Coban, Docker Guatemala, and Kubernetes Guatemala. So thanks everyone for joining us and hope you had a great afternoon. Thank you, Dave.
Thank you. Bye.
Thank you, Dave.
Bye-bye.
Bye.
Bye.